This is sample 7-7, work those muscles. You can see it on page 301 in your textbook. So in this sample, we're going to talk about the force that you need to exert on a spring, and likewise the force that spring exerts on whatever your object is, how much energy can be stored in a stretched or compressed spring, and how that energy can be converted into kinetic energy. So lots to do in this sample. So we have an athlete stretching a set of exercise cords 47 centimeters from their unstretched length. So that's going to be our delta x. And remember, we want our delta x in meters, so we've got to convert that. And the cords behave like a spring with a spring constant of 86 newtons per meter. Now remember, that means it would take 86 newtons of force to stretch that spring by 1 meter. So that's the information we're given to start with. So remember, the athlete is exerting a force on the object. The spring is exerting that same force in the opposite direction because the object is held at a constant distance from the relaxed length. So the first question is, how much force does the athlete exert to hold the cords in their stretched position? And for that, we'll use Hooke's law. All right, and so the absolute value of this force is the spring constant times our delta x. And in your book, they use D for delta x. It's fine as long as you know what they're talking about. What variable they use shouldn't matter to you. So they just say how much force. So they're not asking for a direction or anything. We're just looking for a magnitude. So this one should be pretty easy. 86 newtons per meter times that almost half a meter gives us 40 newtons. So that's how much force the athlete needs to exert to hold that device 47 centimeters stretched from equilibrium. And if you've ever used like a resistance band for physical therapy or yoga or something like that, you'll know what I'm talking about there. So then part B says, how much work did he have to do to stretch them? So the work that you need to do to stretch or compress a string from a formula that we derived earlier is 1/2 kx squared. So again, 1/2 times 86 newtons per meter times 0.47 meters, 0.47 meters. And if you're worried about the units, well, actually the units are pretty easy here. This meter cancels, and then our Newton meter gives us a joule. So the plug-in chug gives us 9.5 joules. So two ways to look at that. That's how much work the athlete had to do to stretch them, and that's how much work this system is going to hold, right? So let's go on to part C, which says the athlete loses his grip on the cords. We're told that the mass of the handle is 250 grams. So how fast is it moving when it hits the wall to which the other end is attached? So what's going to happen now is that the athlete's done 9.5 joules of work on the handle, if you will, to get it out to that position. So where we're going now is that handle has that much potential energy, which can be converted into kinetic energy. Another way to look at this is now the spring is going to do that same amount of work on the handle to bring it back to original position, since this is a restorative force. So the net work that's going to be done by the spring is equal to the change in kinetic energy. Okay, since the spring force is a conservative force, it's going to do 9.5 joules of work. So the spring is going to do that 9.5 joules of work, and that's going to equal 1/2 mvf squared minus 1/2 mvi squared, right? That's our delta change in kinetic energy. And the initial speed of the handles is 0, right? So really this 9.5 joules equals 1/2 times the mass times the final velocity squared. So don't forget to move the 2 over. Don't forget to divide by the mass. But for your final velocity, you get 8.7 meters per second. Now, velocity means direction, right? So let me look back at the question, it says how fast is it moving. So we don't need to say towards the wall, but that's kind of obvious. That's the direction it's moving. So three things you should take away from this sample problem. Hooke's law here in part A tells us how much force we need to maintain that situation. Part B tells us how much work is done in order to stretch or compress a spring, okay? And this problem would have been exactly the same if this were not like a stretchable band, but a compressible spring, and he pushed the handle 0.47 meters in towards the wall. And then it would be the same amount of force, the same amount of work, and the same final velocity when the spring reverse direction. So make sure that when you're doing these problems, you realize that it could be the same, whether the spring is stretched or compressed. So that's our example for springs, forces, work, and energy, and we'll move on to the next one.